Hello and welcome to this presentation called Condition Monitoring is Not Enough. My name is Jason Tranter, the founder and managing director of Mobius Institute. In this presentation we're going to talk a little bit about the maintenance strategies, a little bit about reactive maintenance, preventive and predictive maintenance, as well as run to failure, condition-based and interval-based maintenance. Then we're going to talk much more about condition monitoring. A little bit about condition monitoring itself and the benefits of improving reliability, but a little bit about the program and how some programs don't actually take full advantage of condition monitoring itself. But the main emphasis is to talk about how condition monitoring relates to reliability improvement and what we can do with the condition monitoring skills to go on and improve reliability. And then we'll go further, because we'll talk about defect elimination, the design and procurement process and how that affects reliability, the maintenance process, inventory management and maintenance and repair and installation and that sort of thing, and then also when the machine is being operated, machine and electrical equipment, when that's being operated, what can we do to improve reliability through all those stages? So we'll talk about all those aspects, but with an emphasis also on condition monitoring and how those skills can be used to not only monitor the condition, but also improve the condition. And then we'll get into a little bit about why so many reliability improvement programs fail. Talk a bit about what we think you should do in order to make that program a success, but a little bit about why it fails. And then we'll wrap it up. Now this is a longer presentation. I hope you can set aside the time to listen to the whole message. And I really thank you for attending this presentation, listening to this presentation. Just a little bit about my personal history, given that I'm telling you this presentation. Firstly, Mobius Institute, firstly, to me, I got involved with condition monitoring and particularly vibration analysis way back in 1984. I was actually with Hewlett-Packard for a little bit, and then started a business called Argo and got involved with vibration analysis and also the development of a vibration monitoring system. Now that's a long time ago, but certain trends have appeared way back then and have repeated themselves again and again and again. And for the first sort of 5 years running Argo, we did certain things. I sold that business to a company in the United States, DLI Engineering, and went on and stayed involved with condition monitoring, but this time in the United States. Argo was in Australia, DLI was in the United States, and so we got involved with new companies there. After coming back to Australia and continuing development of condition monitoring systems, I then started Mobius Institute. And Mobius Institute, as you can see, started in 1999 and still going strong in 2014. We've been very fortunate to win a number of business awards and export awards and product awards, including just this. We are the current award holders for iLearn Reliability and iVibe, the Product of the Year award in the United States. But the main point is, and I should say just with Mobius, we develop training materials, we teach courses all over the world in vibration analysis and condition monitoring and reliability improvement, both with e-learning products and classroom training. The main point to outline all of this detail is that over those years I've seen a lot of companies that ultimately have the goal of improving reliability. They see failure all the time, bearing failures and other sorts of failures, and they deal with that failure. Condition monitoring was seen as a solution to the problem, or at least part of the solution, but for many companies it was the main solution. So none of the maintenance practices really changed. None of the way the machines were being operated changed. None of the ways that equipment was being purchased and designed and stored in the organization and all of that. None of that really changed. It's just that a condition monitoring program was put in place, so instead of being surprised when something failed, you got a bit of a warning. And so being involved with that. Condition monitoring is a fantastic tool, and we've really enjoyed teaching people how to use those tools, particularly vibration analysis. But in the last few years, 4 or 5 years, we've really tried to also present people with how they can do much more than just monitor the condition. So that's what this presentation is about, going much further than just monitoring the condition and doing something about problems that pop up. It's really about improving the condition so that we don't find as many problems with condition monitoring. Anyway, we have training centres all over the world in about 50 countries. Just with vibration analysis alone, we have students from about almost 150 countries now. And what you can see there with the yellow dots is the location of our offices. I am personally from Melbourne, Australia, down here in the southeast of Australia. That's the headquarters of Mobius Institute, where we develop the products and do the certification and so on. Two separate business, but anyway. Enough about us. Let's get on with the topic. So, I want to just quickly go through a review of the typical maintenance practices. We know equipment fails, and the big question is, what do we do about it? Very typically, it's just reactive maintenance. Something fails, we do something about it. Even if we get a little bit of warning, we are really letting the machines, rotating equipment and electrical equipment, dictate what we do from day to day. If there's a problem, we deal with it, we keep the plant going. A lot of people doing a lot of very good work, a lot of hard work to maintain a certain level of uptime and so on, but as we'll see in a moment, not necessarily the best strategy. We can also use preventive maintenance, where we're going to try and basically fix things before they break. If we assume things will break sometime in the second year, then we'll replace those components at the end of the first year and hopefully avoid those failures. Or we can use predictive maintenance, where we'll take certain measurements or we'll perform inspections and try to predict when equipment will fail. If it's in good condition, we leave it alone. But we'll talk much more about these in just a moment. We'll look at precision maintenance much more later in the presentation, but that's certainly a strategy that people look at, doing things like alignment and balancing and just in better ways of making installations so that the machine lasts longer. And then defect elimination. Again, we'll talk about that much more later on. Just on reactive maintenance. Really, reactive maintenance is no maintenance. We're not maintaining the running status of the equipment. We are just reacting and having to repair or replace equipment when it fails. As I mentioned earlier, a lot of people doing a lot of very good work, working hard to keep equipment running or get equipment back up and running, but there's a lot of safety incidents that follow, a lot of energy wastage, but really a lot of downtime, a lot of parts failing when they shouldn't. It really costs the company a lot of money, and that loss of money can impact the ability of the company to continue to operate. Shareholders get upset, government departments get upset. Really, it's not the best way. When we look at this sort of reactive cycle, we have a problem, resources are taken by those breakdowns. Because everything's so urgent, there's often repairs performed temporarily, just quickly. We've got to get the machine up and running again, so we install the replacement motor, let's say, but we don't necessarily have the time to do it properly. We don't have time to do root cause failure analysis to eliminate those root causes, but we do get lots of repeat work because we quickly install the machine and it fails soon. We think there's not enough time to do it properly, yet there seems to be time to do it again and again and again. People might suggest, operators or particularly maintenance people might suggest, wow, if we just made these changes, maybe these failures wouldn't occur. But often everything's so urgent, no one really listens to those suggestions, nothing's improved. But management start to think, wow, financially this is unacceptable, and they look at ways to cut the budget, to save costs, to reduce costs. And the short-term thing to do is to fire people or change the maintenance practices and make them even worse. Sure, he gets some short-term gain, but it's not a long-term strategy. The situation just gets worse and worse. Morale declines, standards drop further, backlog grow further. Any preventive maintenance tasks that are put in place, if there are any, they're missed because there's always more urgent work. And we continue around the cycle. Preventive failures occur, and so on, and so on, and so on. This is a cycle we need to break out of, and it can seem like it is very difficult to break out of that cycle. It's not as difficult as it seems, and that's really what this presentation is about. If you identify why these things are occurring, then you can be proactive with the people you have. So let's get on with it. So let's look at the cycle of reliability, which we will talk about much more in this presentation. We will design, specify and purchase with the aim of achieving a high level of reliability, not short-term cost savings. We will reject defective assets, parts and repairs and spares. We will install and commission with precision skills. We will operate and maintain with reliability in mind. We'll do what we have to do to extend the life of the equipment. We will prevent failures where applicable. So if we have age-related faults, we'll prevent those failures. We will focus, though, wherever possible to perform our repair actions or replacements or overhauls based on condition. If there's nothing wrong with the equipment, we let it run, and hopefully there won't be anything wrong with it because we've taken care of all these issues here. But as part of all of that, we need proper stores management. We need to make sure we've got the parts we need, and we need to store them in such a way that they are fit for purpose when we go to use them. We must have effective planning and scheduling to properly plan the work, schedule it at the right time. This is not just about cost saving and proper management. This all relates back to reliability as well. But we will perform some root cause failure analysis. You don't have to consider that as some inquest or royal inquiry or something like that. It's really just a case of saying, okay, we've had a failure, why did it happen? What can we do to mitigate that? What can we do to stop it from happening again? And, when we find that there are imperfect maintenance practices or operating procedures or whatever, we report it and we improve it. And so we have this continuous improvement cycle. And that is the cycle of reliability. If we keep doing that and keep focusing on these things, then we will have a much more profitable plant. Morale will be higher, the shareholders will be happy, the regulatory bodies will be happy, and so on. The trouble is, if you're trapped in that reactive cycle now, you'll feel like, we don't have the time to use those precision techniques. We've got to get the plant running. But as I mentioned before, how come you have time to repeat the job again and again? You install the bearing, you may have to reinstall a replacement bearing very shortly afterwards, or another sort of fault develops. We seem to always make time to deal with those problems. We just don't seem to be able to make time to do it properly in the first place, and that's one of the things that can change. It's not rocket science, as you'll see. It's really common sense, quite straightforward. You just need to do it, make it a priority. The other thing is, you might say, well, they're trying to save money. Upper management are trying to save money, and I'm sitting here saying that there may be special tools you need to use to do the job properly. You need training to do it properly, and you may need some systems in place to do it properly. But so often, yes, at times there will be investment that's required, but you'll be surprised at how much you can do without much of an investment, if not no investment at all. It's just a different philosophy, organising the maintenance crew a little differently, making sure operations operate the equipment the way it was designed to operate. There's a lot you can do without much of an investment, if any at all. And when you get runs on the board, you will management will say, wow, if we invest a little more in this area, we'll get even better results. So the main issue is you can't cost cut to success. There's a lot we could say on this particular topic. The fact is, study after study after study of companies on Wall Street and Fortune 100 and these sorts of things, companies that just focus on cost cutting for success, unless there's a lot of fat in the organization, it just doesn't work. You need to make some changes, and you need to think about investments that will save costs. Not just save costs, increase production rates. Some companies say, well, we make good money out of what we produce, so cutting costs is not the biggest issue. But it really is, because in the act of cutting costs, you increase your production rate as well, and often increase quality. So if you can sell what you make, then this is a really good incentive. Just briefly, I mentioned earlier with the chart with the stages, just one thing I'd like to expand on a little bit. People talk about reactive maintenance, or we've mentioned enough about that, involving some planning. Your planning is based on condition, proactive maintenance, and so on. Just going further up this path of optimizing what you're doing. But there's one little comment I'd like to make, that there are a few extra stages that aren't often sort of mentioned. One is that from reactive maintenance, you may need to go through a phase of sort of planned reactive. In other words, it's reactive, but rather than just having a maintenance crew that works on whatever, whoever's yelling loudest, whoever wants to do whatever, which job, there is a way to begin to organize that reactive response, and then go a step further and say, well, we recognize that there are some age-related faults. There are parts that wear out, and we'll talk a bit more about that. So we can use our planning tools to plan to make changes that are sort of proactive in nature, replacing bearings before they fail. There's a lot more about that particular topic that we'll address in a moment. And last but not least, we will talk much more about condition monitoring, and using condition monitoring to detect when there's a problem. Just detect that there's a problem, and then we react to it. Instead, we can go a bit further and say, well, let's separate monitoring condition to actually basing our maintenance plan. And we need to perhaps go through this transition, but certainly make sure this is working properly, that we can plan when we do have interval-based maintenance tasks, but we also base our maintenance on condition, not just react when the condition monitoring group finds that there's a problem. So just briefly, it's worth considering, well, why do we need to improve? What is the business case for all of this? Now, like a lot of things I'm going to talk about in this presentation, there is a lot we could say on this topic. Lots of research, lots of case studies. Because it's not the main focus, I'll get to the point a bit more quickly. First thing is, we can look at, what is the ultimate goal? Increase profit and shareholder value. But, how do we get there? We can get there by increasing the revenue, and we can do that by increasing the availability. And one way increased availability is that we reduce the downtime, as shown here. As I say, I'm not going to talk too long about all these things. There are other topics we need to get onto, but we are also going to increase availability by achieving the design reliability. Now, there's a certain reliability inherent in any piece of equipment, but we should be looking at what we can do to at least achieve the reliability of the equipment that we receive, but better yet, improve the reliability, through cleaning and proper operation, and there's lots of ways to do it. We can improve the reliability and then go further, as we'll discuss later, to get even better results, because what we're bringing into the plant is in better condition and better designed for the application. And we can increase capacity, so we can look at efficiency improvements by eliminating idling and minor stoppage losses, and improving quality. So we've got a certain availability, a certain amount of time that we're producing a product, but what we want to do is produce saleable products in that time that we're producing. And we can look at capacity or capital investment, increasing it, but we can both look at doing that and see how we can avoid doing that by revealing the hidden plant, you might say. Then look at how we can, okay, we've increased revenue in a number of ways, but let's have a look at how we can reduce the costs as well. So one thing we can do is look at how we reduce expenses, and there are lots of ways we can do that. We can either control or reduce labor costs, and that might be associated with overtime labor or contract labor that has to be brought in for certain tasks, but that's in the area of maintenance, operations and engineering. But the costs associated with materials, well, contract as I mentioned, warranties, energy, EH&S, environmental health and safety, violations and fines. All of these areas are opportunities where we can reduce costs, not by simply slashing the budget and saying you got to work with less money. It's just that if we improve reliability, these are all flow-on effects. And last but not least, we get to reduce the capital investment. Now I mentioned some of that just a moment ago, but we are going to extend asset life. We're going to reduce or eliminate equipment investments because we're achieving the design capacity. So if greater capacity is required, there's a lot we can do before we even need to sort of think about expanding the plant or doing anything else. So these are really important areas. Jeff Dudley, who developed some of our training product, he was the Corporate Reliability and Maintenance Director at Dow Chemical, and he puts it very simply. Organizations with poor reliability practices waste 10% of their revenue, waste 15% of their resources, they disappoint customers, they disengage customers, and they constantly deal with new and repeated unplanned events. Now, a lot of what we're talking about, flows back into this, why this happens and what we can do with it. But he was involved with so many Dow Chemical plants, and that was his conclusion, looking at so many plants and plants from outside as well. I mean, they are some really important numbers. The Aberdeen group have performed a lot of research, really worthwhile taking a look at some of that research. What they did by a lot of surveys, they categorized companies as being the sort of the best in class, the mid-range, average performers, and the laggards. And you can pause the movie if you like and sort of look at some of these numbers, what their OEE was, what they achieved, return on asset versus planned, and so on. The real key with this is that when you compare the laggards, which you can decide whether you're which of those groups you're in, but let's compare the laggards to the best in class. The laggards the best in class enjoy less than a tenth of the unscheduled downtime. A tenth. They achieve 26% higher OEE. They reduce their maintenance costs by 30%. They outperform corporate expectations by 20%. They achieved 2.9 versus 5.4 asset downtime due to safety or environmental incidents. They achieved 15.1 versus negative 8.8 operating margin against corporate plan. And you can see the numbers for total energy consumption. Now they are really compelling numbers, and you will see in this presentation there are a number of ways to achieve it, a lot of small steps, but this isn't through some huge investment, not the way I am here to present it to, and I'll just say what we do in our training, how we train people to tackle this problem. These were some numbers from an IBM presentation just recently. Looking at the potential cost savings by going through this sort of a process. Labor utilization can be up 10 to 20%, asset utilization up 3 to 5%, increased planned maintenance by 50 to 80%, new equipment purchases down, on-hand inventory needs down, material costs reduced, and purchasing labour, contract labour down by 10 to 50%. Again, these are all really impressive numbers. These are numbers you should aspire to try and achieve. So we will see how we can achieve those. Safety and reliability. Everyone, particularly at senior management level, but everyone is interested in reducing the number of safety incidents. The fact is that when a machine fails or when there's an electrical fault, there is a chance of a safety and environmental incident just right there because of the failure. It can lead to a safety incident. But the other thing is that any time someone is spending time working on a machine, if you're involved with electrical equipment or mechanical equipment, there is a higher likelihood of a safety incident. It is more dangerous around the machine. So, and particularly if you're in a reactive maintenance mode, work is being rushed, potentially unskilled workers are doing that job. You may identify someone who should do the job, but they're working on another project and now they're not available for the job they should be doing perhaps. There's not adequate planning, they're using the wrong tools, etc., etc. The bottom line is there is a direct correlation between safety and reliability. The higher the reliability, the lower the number of safety incidents. In other words, high reliability, high levels of safety. So, one more comment is, energy consumption and product quality are also affected by improving reliability and condition monitoring. I've listed some examples here. So properly balanced, aligned and lubricated machines consume less energy. Eliminating high resistance joints and voltage unbalance and line harmonics result in lower energy consumption. Properly sized motors and pumps consume less energy. You can detect and correct leaks and steam trap faults. Properly tuned PID loops result in less energy consumption and higher quality. Now you've got to look at your industry and your situation. Generally speaking, lower vibration levels result in higher quality. Now again, that depends on what it is you're producing, but certainly a plant with a reliable culture will have higher quality products with reduced rate of rejection and rework. So savings in energy, improvements in product quality. Again, it's going to depend on your particular industry. So let's revisit the question of maintenance practices. We're going to describe them a little bit differently. Instead of just talking about reactive maintenance, which is just the way all maintenance is being done, we're going to choose to have some equipment that we allow to run to failure, and I'll mention more about that in a moment. We are going to identify some equipment where we are going to perform interval-based maintenance. It's going to make sense because they are age-related faults to schedule the maintenance, some replacement task on a time basis or a number of running hours or kilometres travelled or whatever it happens to be. But for a lot of our equipment, which generally speaking may be 80% of equipment, but that's going to depend on your industry, we will implement condition-based maintenance. So some we allow to fail, some we provide maintenance on an interval basis, but the rest we have condition-based maintenance. And we will identify some equipment that doesn't conveniently fall into any of those categories, and we will look at a redesign. And then we will, as a general statement, we'll have proactive maintenance. But it's much more than proactive maintenance. I'll be talking more about it, defect elimination. So before we can really talk about that too much, we need to understand a little bit more about failure modes and failure rates. So if we look at a family of equipment, motors and pumps and so on, how does that equipment fail and why does it fail? In many cases, the when someone's trying to break out of reactive maintenance, their thought is, well, I need to get ahead of the curve. If we can plan the maintenance before it fails, then that's ideal. And that is ideal, to plan the maintenance before the equipment fails. Where that goes wrong is there is an assumption that you can accurately predict, just simply based on running hours, let's say, that when the equipment's going to fail. And unfortunately, that's not necessarily true for the majority of your equipment. And I won't dwell on this topic because we do have other presentations on this. But the general feeling is, if we look at the y-axis here being risk of failure, there's always some risk of failure, but after it's been overhauled or repaired or replaced, that risk will be low. We'll go through some period of time, and then finally, if we look at just an individual piece of equipment, something happens such that the bearing's damaged and or wear begins, and the risk of failure increases and increases until finally it does fail. And we can look at a whole family of motors driving pumps and say, yes, that is what we expect. And based on that, we might say, hey, well, if we replace all the bearings and seals or whatever you decide is appropriate at 12 months, then all we do is we have this trouble-free operation. We perform that maintenance task, and then we reset the clock, and we just keep in this mode. And that would be lovely if it were true, and lovely if the equipment was going to fail soon after, and that's what we've avoided. But that, unfortunately, is not the case. First, we have to consider that there's infant mortality. Generally speaking, depending on your maintenance practices, the worst thing you can do is touch the equipment. Once you open it up and go to replace a bearing, even if that equipment was in perfect condition beforehand, there's a chance, unfortunately quite a good chance, particularly in a reactive environment, of introducing some sort of problem. The bearing's not installed properly for one of a variety of reasons. Lots of things can go wrong. So in actual fact, when we go to start that machine, there is a much higher risk of failure. And it can take some time before we can really say, all right, the risk of failure has reduced, we've survived that infant mortality period. And now we're just operating the machine through this period of relatively low risk of failure before it naturally begins to fail, because we're assuming they're age-related faults. But because there are so many reasons why equipment fails, again, if we just look at our motor pump, there are so many reasons why the bearing might fail that we really don't know when the failure is going to occur. We call that random failures. It could occur after 6 weeks, 6 months, 6 years. It could be anything, because we don't really know how bad the alignment job was, how bad the bearing was installed, how much misalignment, how much, unbalanced, how bad the lubricant is. We don't know. So looking at any one piece of equipment, it could wear out after this much time. This is just one piece of equipment. It could wear out after that time. When I say wear out, fail. That much time, we just don't really know. That's why we say it's random, because looking at a family of equipment, the amount of time it takes for something to fail is going to vary. Even if we look at the history of a single piece of equipment, if we don't have very good maintenance and operating practices, then we can really say it is random, because we can't predict the time. It may become more predictable if we control all of our maintenance practices and so on, but that's another story. So just to continue the story, you would expect that if you took 30 bearings, ran them all, as they're supposed to be run, then they will all last a certain number of operating hours. You will achieve a certain number of revolutions, and then they'll all begin to fail. Now, the idea is then that if you were to replace those bearings after this amount of time, you're wasting a lot of money. If, on the other hand, you wait too long to perform the maintenance, well, they're all going to fail. So if we plan it just right. Maybe we collect all mean time between failure data or something like that, and we say, right, this is the time to replace these bearings because, okay, some would have gone a little bit longer, but we're not really wasting much money. That, unfortunately, is not the reality. These are the results of an actual study. Now you can see that some bearings failed rather quickly. Some lasted a very long time. Now it's not to say that your results are going to be as dramatic as these, but the bottom line is that it isn't a consistent age that you're going to achieve. It isn't a consistent, predictable age that you're going to achieve. So you certainly don't want to be maintaining or replacing these bearings to avoid any failures, because these bearings lasted a lot longer and you're wasting money. But of course, the longer you leave that planned maintenance or that preventive maintenance schedule, you therefore are accepting that certain bearings will fail and certain bearings won't. And this really is the premise for condition-based maintenance. If we need to replace this bearing, we will. But this one we won't until we get to 280 million revolutions. So not that we're going to get into how many revolutions we're achieving. The bottom line is, if we look at the condition, we can respond. I almost said the word react, because condition monitoring is a little bit like an advanced form of reactive maintenance. We're determining that there's a problem and reacting to it. But at least we don't allow the failure. We can plan it, plan the maintenance for the most convenient time with the lowest costs. But if we can improve the maintenance practices through the techniques that I will talk about, we can increase the life of these bearings as well. And without going into details, there have been a number of studies. Now, this was the original one from Nolan and Heap many years ago. There have been lots of studies that have basically come up with these same results. Maybe a little bit of variation depending on the amount of infant mortality. But in the original study, 68% of all the equipment had this failure pattern. Infant mortality, so a high risk of failure right at the beginning. When you survive that, failures were random afterwards. In this case, they were just purely random. There wasn't a higher probability of failure at the beginning, but just completely random. And in this case, there was actually a lower probability at the beginning. So here we've got 89% of all equipment with this random failure pattern. So therefore, one would assume that roughly that same percentage of your equipment should be on condition-based maintenance, not time-based maintenance. So what we want to do with our new maintenance and operating practices and everything else that I'll talk about, we would really like to improve our condition monitoring process so that we can detect the fault as early as possible. The earlier we detect that fault, the more time we have to plan. We can make certain decisions related to the spares inventory and so on. We can plan, we can find the best time to perform the repair and so on. What we also want to do is extend the life of the equipment. Yep, detect the problem earlier, but make the detection of the problem 9 years, not 9 months or 9 weeks. And finally, we're going to change our maintenance practices to greatly reduce that risk of infant mortality. So that's something else we want to do. And again, all these defect elimination techniques that I'll talk about, achieve that goal as well. So I mentioned that run to failure is still acceptable, but only under certain situations. The equipment is not expensive to replace. It doesn't pose a safety risk. They're not critical, and of course we'll perform an asset criticality ranking in order to determine what's critical. That failure doesn't cause secondary damage, and you carry spares, or you can get them easily enough such that when there's a failure, it doesn't really matter. And therefore you can't justify either performing condition monitoring or preventing failure by replacing parts on some sort of interval. And it probably isn't justified to perform root cause failure analysis unless you find it easy to do and you know why it's happening and you can make some sort of an improvement. But ultimately, equipment like that you can run to failure, and that's a sensible thing to do because you'd be wasting money to do anything else. You still might make sure that you install it properly, and if it requires lubrication, do that properly. Consider what spares are required and how important it is to have these sorts of spares. And if you hear that the fan's making some awful sound, you might still repair it before it catastrophically fails, or replace it. That's up to you. But then we can look at interval-based maintenance. Now, here is the situation where we are confident that if we perform a maintenance activity based on the operating hours or the kilometres the trucks have gone, or just based on calendar, that is the most appropriate strategy. And I'm sort of talking about it in this order. In other words, not talking about condition monitoring and condition-based maintenance now, because I'm going to talk much more about condition-based maintenance. But the bottom line is we should really try and do condition-based maintenance, and if that's not possible, use this technique. So basically, if they are age-related and we cannot detect them with some sort of condition monitoring technique, then we should try and prevent them. If we know that it takes a certain time for this particular cog to fail, then we'll just schedule its replacement in the time. But when we talk about preventive maintenance, I've sort of deliberately not used that term because it can be used in very different ways. So that's why I'm talking about interval-based maintenance. The act of performing either a classical condition monitoring task like vibration analysis on some time schedule, or performing an inspection, I'm going to lump all of those tasks together as condition monitoring or condition-based maintenance. So going out there and looking at the cogs and looking at the teeth, I consider that condition monitoring. It's you performing an inspection, and your maintenance decision to repair it, to replace it, whatever's applicable, is based on its condition, not based on a time interval. So you have to think really what tasks, what assets do you have that really do fail based on a time interval. In this case, talk about tyre wear. We can say that that's an age-related fault, but different drivers might achieve different rates of wear. Better drivers might have the tyres wear less, depending on road conditions, weather conditions, all sorts of things. And therefore, again, we can inspect the tyres. We may plan to, have in the budget to replace those tyres on a certain interval, but ultimately we can perform an inspection, and if the tyre's still good, we don't replace it. Those decisions are ultimately up to you. Even things like, replacing filters. You may still find that your monitoring system has a way of looking at differential pressure and tell you whether the filters needs to be replaced, or you can do a visual inspection. It's still condition monitoring. But if you knew for sure that, hey, every 6 months or every 2 years or whatever the case is, those filters should be replaced, or whatever the item is, then that's where interval-based maintenance makes sense. The problem is that a lot of people are performing these maintenance tasks when they're not really necessary. It's a bit of a contentious issue, but sometimes vendors and OEMs might tell you to perform certain tasks. How can I choose my words properly so that it suits them? They want to sell you their parts, they want to sell you their service person labour and all that sort of thing. Sometimes you need to look really closely at those maintenance tasks you have in your system now and see, are they really adding value? In many cases they may not be. And of course, tasks should be more useful than just saying, hey, check pump. What is a person checking? Alright, just for a laugh, the pump's missing. Oh, they actually did detect something this time. But you've got to make sure that PM tasks, planned maintenance tasks, are actually useful and adding value, and have a way of reporting back that some sort of work is required. Because any time we perform an intrusive task, we have the likelihood of damaging the equipment. Okay, having a joke, you drop a flashlight or a torch inside and it damages the teeth, or, but it's true. You open a machine, you increase the likelihood that you're going to damage it and therefore reduce its reliability. So let's look at condition-based maintenance. We know from a lot of experience and so on that the equipment, there might be problems, but the equipment warns you. The ultrasound tells you there's a leak. Ultrasound and infrared ultrasound tells you there's arcing. Ultrasound might tell us that there's a need for grease. Vibration might tell you. There's lots of different condition monitoring technologies that tell us what the condition is, and we can act on that. So we have the more classical techniques: vibration analysis, ultrasound, thermography, oil analysis and wear particle analysis, motor testing, dissolved gas analysis on transformers, partial discharge, and there's lots of other sort of classical techniques that may require some special instrumentation and some expertise. But we can also perform inspections and make observations. Operators can be asked to not only keep an eye out for problems, but specifically go and look for oil leaks and bearings that feel hot and so on. And then we can also use performance monitoring to look at the performance characteristics of a compressor or a pump, looking at flows and pressure, and see, okay, it seems to be okay from a vibration point of view, but in actual fact where it's not performing the task correctly, it's not efficient, and it may have sort of functionally failed. It was there to perform a certain pressure and flow, achieve a certain pressure and flow, and it's not doing that. So the whole idea of condition monitoring can be summarized by a chart like this. Now this is sort of the inverse of what we were looking at before. Here we've got a high level of condition, and this is good. We want a high level of condition, and the equipment operates with that high level for a certain period of time. Something happens that initiates a defect. To keep it simple with bearings, that could be a contaminant that damages the inner race or outer race. It could be any number of things. The defect is initiated, and then we get to a point where we can actually detect that defect. And at that point, we mark that as the P point for potential failure. It's now detectable, and there is some risk of failure. And if we don't do anything, the condition will get worse and worse and worse and worse until it ultimately fails. We might identify some point before that time, which we will call, the point of functional failure. It's no longer able to do its job. It has functionally failed, even if the bearing hasn't sort of seized or something like that. Now, the idea is that we can use all of these technologies, and they won't necessarily detect it in this order. Vibration might be first, oil analysis might be first. Let's not discuss that right now. But the fact is, what we would like to do is detect it as early as possible, because the earlier we detect it, there's a lower risk of failure, a lower cost of repair or replacement, and we've got much more planning time, so that's good. The longer we leave it, those costs go up, the risk goes up, our planning time is therefore going down until it ultimately fails. This is a situation, if we use the condition monitoring technologies correctly, we will detect it early, keep our costs down, and be able to do a good job with planning. What we'd really like to do actually is avoid all of this or postpone it. It's great that we can detect it, it's great that we can keep our costs and risk down, but really what this presentation is about is doing much more than that. So in this case, what we're going to do is try and maintain this high level of condition, and if we lubricate it properly, align it properly, and all these other things that I'll talk about, we will achieve that much higher level of reliability. It'll keep a high level of condition, and this might all happen after 10 years rather than 10 weeks, as I've mentioned. Okay, question is, how do we make all those decisions? How do we decide whether to let it run to fail and all that sort of stuff? Some people will say at this point, you need classical RCM. You need to really look at every piece of equipment and consider all the failure modes, not just the equipment, look at it as a system. What are the failure modes and the effects? What are the ramifications of failure, and so on. We could talk about classical RCM for a long time. I've used this guy with that expression simply because on the one hand, a lot of people have tried and failed, and I'll mention that a bit later, but also a lot of management are a little bit wary of RCM. Now, I don't want to say it's a controversial topic. Some people have very strong views one way or the other. The truth is that taking a classical RCM approach can suck up a lot of time and resources, and sometimes there is no result as a result. There is a more streamlined way to come to these conclusions without going through this really detailed process. There's a lot more we could say about that. That's enough for now. What I'm just going to briefly mention is that ultimately we're trying to develop this reliability strategy. Which ones can we allow to fail, and then we'll have run to failure? Which ones can we predict, and we'll use condition-based maintenance? Which ones can we prevent through some age-related interval task, and we'll use interval-based maintenance? And if we can't prevent it, we can't predict it, but we don't want to let it fail, then we need to consider a redesign. But how do we make those decisions? Well, at the very least, you need a master asset list. You need to perform an asset criticality ranking so that you can prioritize all these sorts of decisions. You then need to think about the failure modes, the risks, the detectability. You can go through a practical process of making these decisions. In the interests of time, I won't elaborate too much on it, but rather than just saying I'm going to buy a vibration analyzer and start measuring things, you'll get a return on investment. It might be a satisfactory return on investment. You will achieve much better results if you go through this process. There's a lot more to this. I won't go into all the details right now, but certainly having leadership and having this driven from the top is a good idea. Having a plan and a vision to make all this happen, considering all the culture change issues and so on, is an important thing, and training. And as I say, I'm not going to dwell on this. The ultimate goal is to get to this point where we can have proper procurement, stores, inventory management, planning and scheduling, precision skills, operator care, and root cause failure analysis. And then we want to look at a proper continuous improvement program. Okay, just to dwell a little bit on asset criticality ranking. A lot of organizations really struggle with this because there's this argument about which is most critical on a very simple measure. How would I feel if it failed? Well, we don't want it to fail because it can stop production, and there might be thoughts about the safety implications or the cost of repair or replacement. Just looking at the importance of a piece of equipment makes it very hard to decide which one's more important than another, because there's a lot of equipment that we can easily say is very important because it can stop the plant. We need to go further. We need to break that decision up into its component parts. We need to get agreement. But what we need to understand is that criticality is not just importance. It's not just about the consequences, it's about the likelihood of failure as well. So if we can assess that two pieces of equipment are equally important to us, the consequences are the same, but one has much better reliability than another, then, in other words, the likelihood of failure is much lower with one than the other, then the one that is more likely to fail becomes more critical. And this is a table from one organisation. I won't go into the details to come up with a ranking. There are other ways to go about it, and so I wish I had more time to talk about it. So talking about your condition monitoring program, the question is, how good is it? How effective really is it? How did you decide what test locations were used? Like, where on the motor and the pump and so on, where are you taking measurements? And what axes, horizontal, vertical, axial, what are you using? How repeatable is the data collection? How were the settings of, Fmax and resolution and all those sorts of settings, how were they chosen? How were the alarms set? Have you considered that different machines vibrate differently because of their stiffness, because of the way they're mounted, the speed, the process, all these sorts of things? Have you thought about the actual PF interval? The time between tests should be based on the PF interval, not criticality. Do you have certified analysts? Now, I'm biased. We're involved with training and certification and so on, but those standards are there for a reason. You should have category 3 people involved in managing the program. We can look at where oil samples are taken from, and is there any chance of contamination? So all of these are really important points. People sometimes say, oh, I do a great job with my vibration program and I use the latest technology, but you see them taking measurements like this. That is going to be a poor measurement. This one, a person's taking vibration readings, but the thing's covered in, some sort of dust, or, maybe it's a cement mill or something else. Now, yep, you've got to take the measurements, but, why not be proactive and say, well, having a machine covered like that will reduce its reliability, so let's keep it clean. Don't just monitor and wait for the bearings to finally fail or something else. There's other little details. People are in love, a lot of people are in love with infrared analysis. It's a great technology. A person could easily make a diagnosis that there's a problem. In actual fact, that's just a reflection. That's the heat of the operator, not the heat of the electrical piece of equipment there. Someone has spent some money to buy containers to dispense lubricant, but look at the condition of it. All of these containers here are being stored outside at an iron ore mine. So much contamination is going to occur. Bearing installation, just for fun, there he is with a hammer. He's giving a good old bang. It's not the best way to do the job. It's just not the best way to do the job. An appreciation often doesn't exist about the need for the right tool and how to use those tools. Here's someone with the right tools. They've got a laser alignment system, but look at the way this motor is mounted. There's no way they're going to get good reliability out of this thing. That thing's going to move all over the place. It's just, a disaster. But, well, he's using laser alignment, so it's, it looks good. And then even with even if you're doing condition monitoring properly, the question is anyone listening? Are the maintenance planners actually listening to you when you say there's a problem? Do they believe in the technology? Is the philosophy that we will, plan properly when the condition warrants it, and not based on calendar? Just as a little detail, there are a lot of ISO standards out there that talk all about how people involved with condition monitoring should be trained, what experience they should have, and the whole certification process. Again, I am biased. We offer certification and we're accredited to these standards and so on, but they are there for a reason. We went down that path for a reason. There are lots of other standards that describe how the program should be run, how machines should be tested, lots of things. There are a very large number. There's just 3 of them. I am personally part of this ISO Technical Committee 108 Subcommittee 5 that writes these standards, and then Subcommittee 2 is involved very specifically with vibration related standards, amplitude levels, things like that. Now the ISO standards, they're It's an interesting process developing them, but the goal is that we bring people from all over the world to discuss these different topics and come up with a consensus. Then it goes back out to all the different country bodies for them to vote. Sometimes, actually at the time that I'm recording this, I was in Paris last week for one of these meetings, and sometimes they get a little bit heated.
Dovolte, než začnu moderovat, vyřídit si jednu zcela soukromou věc. Děkuji. Pan minister rád byl předem varován, varoval jsem ho tiskem, je to moje ryzí soukromá záležitost. Zaslouží si to. Pane doktore, tady to vyřizovat nebudem. Vy jste mě napadl zbaběle ze zadu. Proč jste se mi nepostavil jako chlap čelem? Vy jste zbabělec.
Okay, the ISO meetings don't really end up in fist fights and all of that. This is just a joke, obviously, just from some other political meeting or something like that. Anyway, just having a bit of a laugh. But the ISO standards are very important, something you should take a look at. But with everything we've primarily been discussing so far, we're really just talking about how we manage failure. We accept that equipment fails, and our whole focus is on getting ahead of it, detecting it, and then dealing with it. And I talked about reactive maintenance versus condition-based maintenance and so on. But, you know, you could say that condition-based maintenance is just glorified reactive maintenance. We just get to react a bit earlier. It's very valuable. There are a lot of benefits, but we are just reacting early to the problem. So, you know, we've got the choice. We either let it fail if that's acceptable, we get advanced warning of the failure, or we hope to fix it before it fails. You know, does condition monitoring actually improve reliability? You know, it depends on your perspective. If you consider reliability, how often your equipment fails, how much you have downtime because a piece of equipment has failed, well, because condition monitoring can prevent that, it gives us the opportunity to plan the maintenance. Then you can say, yes, just basically monitoring the condition and dealing with it on our terms is an improvement in reliability. But many of the condition monitoring technologies actually does not improve the inherent reliability of the piece of equipment. I like to describe condition monitoring as sort of a number of layers, and I would argue that most people really just deal with it at this primary layer. It's just fault detection. We are looking for problems, we find the problems, we deal with the problems. If we have a proper condition-based maintenance program, then we can go a step further and say, well, we're not just reacting to problems, we really are properly performing our maintenance based on conditions. So that's a good thing. That's a good thing. And this is where we start bordering on reliability improvement. But you know, it's using condition monitoring for quality control. So when a piece of equipment is repaired, we can test that piece of equipment. And I'll talk much more about how condition monitoring can be used for quality control as I go further. And you know, as I mentioned earlier, we can get an early warning. We can reduce the maintenance costs. We can enhance the planning process. It is valuable just looking at it from a sort of a QA point of view and a maintenance planning point of view. So how do we deal with poor reliability? Now, being very simplistic about it, I'm going to say that I see three broad approaches. One is to analyze it, and I don't mean to be too flippant about it using that image, but a lot of people's first approach is to try and gather a lot of data to understand the true reliability of their plant, considering redundancy and, equipment in series, equipment in parallel, and all that sort of thing, to try and understand, what their likelihood of being able to achieve a certain level of utilization. A lot of time and money can be spent trying to do that analysis, but sometimes I feel like people are just accepting the reliability of the plant for what it is, and if they find any vulnerabilities in reliability, they look at what they can do about that, new pieces of equipment or whatever, or just looking at what their utilization is going to be. Sometimes a lot of time is spent using random data that wasn't collected very well in the first place, and then making all kinds of important decisions about it. And sometimes, now you have to wonder, you just have to answer the question yourself whether this is your situation, but people will, I will ask people, well, how are you making these decisions? Okay, based on this data, we've got some mean time between failure data. How good is that data? Oh, well, actually, not very good. It's not really reliable data. Well, then why are you making those decisions with that data? Well, we don't have any other data, so we just have to use this data. But, there's a little bit of a flaw to that logic. You're using very flawed data and then making decisions on it. And again, we get into this circular discussion. Well, but I don't have any other data, so I have to use that. But if you consider just how random some of those mean time between failure stats are, you've achieved a certain level of reliability thus far. Who's to say that what's happened in the future is going to look like how it has in the past? That's really important to look at, the statistical analysis and so on. Anyway, I won't say anything more about it. We can also look at, just dealing with it from a maintenance point of view. Something breaks, we fix it. We perform some tasks like lubrication and so on to maintain its operation. And I would argue that to some extent, to a large extent, reliability-centered maintenance focuses on this. It suggests that maintenance is responsible for the reliability problems. That on the one hand, if we improved our maintenance, we would achieve better reliability, and if we've got better maintenance, then we are better able to deal with poor reliability. Now, it's not to say that we don't want better maintenance practices, and we don't want a maintenance crew that's able to deal with the problems, but I just think the focus has got to be on improving the reliability. Don't just accept the inherent reliability that you've experienced thus far. That doesn't have to be your future. It does not have to be your future. So I'm going to add another layer where we look at condition monitoring and we see how we can use it to proactively improve reliability. And one of the best techniques is defect elimination. So let's explore defect elimination in more detail. Unfortunately, I can't really go into every single detail in a lot of depth. This is just supposed to be a couple-hour presentation, but let's go on and have a look at it. We're going to look at how we can improve reliability and utilize our condition monitoring skills to contribute to that improved reliability. The way I like to look at it, now again I'm looking at rotating machinery rather than a piece of electrical equipment. We want to take care of that. I've drawn it here on a pillow. We want that equipment to be reliable. We've got to do everything we can to protect it from all the reasons why it becomes unreliable. So we're going to put a force field around the plant, and unreliable suppliers, they don't get into our plant. When I say unreliable suppliers, it also means suppliers who provide unreliable services or equipment. Cheap spares, they don't get into our plant because we know that they're cheap up front, but life cycle costs are terrible. Transportation, you've got something that's in perfectly good condition, hopefully. It's transported to your plant and it's damaged. False Brunelling of the bearings, very common. Unskilled contractors. maybe too willing to just accept that during shutdowns we're just going to let all these contractors come in, do the work as quickly as they can, and they get out and they're not held accountable. You've got to stop that if you want to improve reliability. Designs of equipment. Who is making a design with life cycle costs in mind? Maintainability and reliability. Once we've done that, we are stopping, and procurement process is part of that, and I will elaborate on all these things. Now hopefully what gets into our plant is worthy of your plant. You haven't bought anything, you haven't contracted anything that's unreliable. What gets in your plant is good. Now, how do we protect the machine further? Because what we need to do is we've got to keep contaminated lubricant out of that machine. We can buy good lubricant. We can also buy poor lubricant, but we can buy good lubricant that becomes contaminated, and we don't put that in the machine. We don't damage parts while they're sitting on the shelf and then try to put them in the machine, or we don't damage them in the process of putting them in the machine. And as part of that, we don't accept poor installation practices. We've got to protect our machine from that. We've got to protect our machine from poor operating practices and unnecessary PMs that just induce problems, and intrusive inspections that induce problems. And finally, we're going to do true maintenance, you might say, by cleaning it, adjusting it, replenishing various lubricants and so on, and we will monitor it. We will watch over it and say, we've protected you as much as we can, but wear still happens, and problems still happen. And when that happens, we are going to monitor it, deal with it, use root cause failure analysis to see how it got through and harmed our machine. So that's the basic idea of defect elimination. So let's talk about it a bit more. I'm going to basically break it up into three areas. When it's operating, when we are installing the equipment or overhauling it and storing the equipment. Did I say that? Installing. And the procurement and design process. So we have to look at our procurement process and the design decisions we are making so that the life cycle costs are prioritized over the upfront purchase costs. And we have to put a barrier, as I just showed, around the plant. So, number one, how are you going through the design process at the moment? Are you designing for reliability and maintainability? Often the answer is no. And then we can look at energy efficiency, but we have to look at how, for example, a motor is rated. So often motors end up being put in place that are rated well above what they need to be. That is not good for the motor. It's not good for the motor. A motor is designed for a particular task, and therefore the correct motor should be specified and purchased and installed. It is very important. As I say, motors are designed a certain way, and that's how they should be operated. Same is true for the pump. We're expecting a certain flow and pressure, and that's how the pump should be specified. We shouldn't over-specify it, and therefore the pump isn't operating at its best efficiency point. All these topics we could talk about, with more detail, but we don't have time. If we operate it with lower flow than we should, then we damage bearings and seals, we affect the impeller, we have cavitation and temperature rises. If we have too high a flow, then again we affect the bearings and seal, and we have high flow cavitation. We need to operate really close to the best efficiency point. Later on I'll mention this again because that depends on how we actually operate it, but at least we need to purchase it so that we can operate it at its best efficiency point. The purchase process is also so important. Again, I talk about the life cycle costs, but what is the goal of the purchasing department? Usually, it's to buy equipment at the lowest possible price. And that is an important goal. You don't want to just, spend more money than you need to, but what we have to do is set the bar higher. We need to have the least expensive product that meets a much higher standard. So we have to put those standards in place. And you have to be very careful about what you're buying. Counterfeit bearings, I'll mention a bit more about that in a moment, but lubricants that don't meet spec, flimsy pumps and fans, and inefficient motors, and equipment with poor reliability and maintainability. If you're not already familiar with it, counterfeit bearings are a real problem. Counterfeit bearings can look better than the real thing. If you just did a normal inspection, they can look better than the real thing, but they are not better than the real thing, not by a long shot. And you may have them in your plant right now. When you have failures, you may wonder why you're having those premature failures, but counterfeit bearings could be part of the reason. You need to be aware of just how big a problem this is right now, and not just bearings, oil filters, lots of things. You just got to think, where is it coming from? How's it been designed, engineered, manufactured, and all that sort of thing, through that procurement process. The equipment, you may think it's fine, but how's it been stored and treated? All very, very important. This also goes for the people outside your plant who do work for you, like motor rewinds and balancing and so on. What specifications are you putting in place to make sure that they're doing the best possible job for you? Is it the lowest cost bidder? When you send a rotor out to be balanced, what specifications are you putting on that? Are they just balancing it and giving it back, and the vibration's lower, but is it as low as it could be? Are you using ISO standards to set this? And it goes for rewinds and all the rest. You need to know what it is these suppliers are doing, and you need to tell them, well, this is the standard I expect. Otherwise, you will end up with problems, and they will be your problems. Okay, some things might be under warranty, but a lot of times, if it doesn't happen right away, you're left holding the can. So it's very important to put these standards in place. The next one is transportation. Again, equipment can be damaged as it's being transported to your plant. And now, these particular companies, ignore that. When they're being transported, bearings can be damaged. Water can get into components if it's being shipped, salt water and so on. But just the process of being transported, we can have false Brinelling. Where all the rollers are, they just chip away, and then corrosion occurs at that point. It's really serious, and the people transporting the equipment need to understand that. And if you don't feel it's been transported properly, then you need to be affirmative about it and just say, well, we're not accepting it. You've damaged it. Now, this is where the condition monitoring stuff comes into it. It's okay to say we are going to set a high design and procurement standard. We're going to hold our service people to a higher standard and all that sort of thing. But unless you're checking it, unless you're asking them to prove it to your satisfaction, well, they may not provide you what you think. And hey, you might even order things and not have delivered what you expected. That sort of thing can go on. So this is where the sort of the quality assurance and quality control comes into it. You need to use acceptance testing. You need to stand there and say, if it doesn't meet our requirements, if it doesn't meet our standards, then it does not get into the plant. And this is an area that some organizations get. Some organizations wouldn't dream of accepting motors, pumps, fans, lubricants and so on without it going through acceptance testing. But I find there's a lot of companies that aren't even familiar with acceptance testing. The sad truth is that a lot of equipment that's purchased is already damaged when it comes into your plant. It already has damaged bearings or contamination or all manner of things. It resonates when it operates. If you buy, a skid, it resonates. If a motor and pump on a skid, they may not be aligned properly. Again, with all these topics, we could talk an awful lot. You can't just assume that it will be of a high quality. You have to mandate that it will be, and you need to provide specifications to that company to make sure that they meet those standards. The interesting thing is, if you purchased a piece of equipment, and this is just a random image of a piece of equipment, and you force them to go through acceptance testing, and this piece of equipment is rejected, you will get one ultimately that meets your standard. The vendor will make sure that you get the equipment that meets your higher standards. But that doesn't mean this is going to be scrapped. Your competitor or another plant will get this piece of equipment. So as more people do acceptance testing, you could argue that that increases the probability of people who are not doing acceptance testing of getting equipment that has problems. So bottom line is, there's a lot that could be said about this, but you need to have acceptance testing. The warranty period should begin when the tests have been passed. You need to look at where the tests are done and so on. But basically, there should be an inspection process and a testing process. Some of those tests can be performed at the supplier's workshop. Some tests may be performed at your site. You need to specify measurement location, types of measurements, sensors to be used, etc., etc., etc. Don't just say, please test it. You need to be very specific about how those tests are done. Sometimes the feedback I get is, well, it's hard to know what those standards should say. But you need to be very clear, and there are 3 sources of this sort of information. ISO standards, there are some guidelines published just generally out there in industry, and then people have experience. Condition monitoring people know what the condition should be at the beginning. Go to the ISO website and Google this stuff, but I have listed here a number of standards, and some of these may have been updated. The actual dates that you see here may have been updated since then. I apologize if that's the case, but there are lots of these standards that explain, okay, this is the way to set up acceptance testing on these types of equipment. Likewise, you can set it up, there's more standards. Likewise, for balancing, you can specify, okay, for a particular speed that's along the x-axis, for a particular balance grade, that's what the residual unbalance can be. Without going into detail, it just means how much unbalance will you accept for a rotor of a particular weight and operating speed. But here's the key. Specify G 1.0, not G 2.5 or 6.3. Go for G 1.0. But if you Google this, you'll find that this standard's publicly available out there, and it goes through and talks about measurement locations and all kinds of things, vibration amplitudes and so on. It's good. There's a NASA standard out there that you can find. Anyway, so look for these things, set up the standards. Don't assume that what you get from the suppliers is in good condition and fit for your purpose. Now let's look at the next category. Now we've stopped unreliable equipment from getting into the plant. Now we've got to take care of it and make sure we install it properly as well. We're putting a barrier around the asset itself, the machine or the electrical switchboard or whatever. As part of this, we need efficient spares management and improved work practices. As always, there's lots we could say about this, but number one, we really need to optimize the inventory. Think about what you store, what gets stored sort of on consignment or whatever at another supplier, so that you can minimize it, but through a criticality ranking you know what you need to keep. But you have to make sure you do not introduce defects into that equipment while it's in inventory. So you need an asset criticality ranking that I mentioned before to make sure you're keeping the right spares, and then you need to take a look at how you're keeping them. This motor is not going to be in good condition when it's installed, nor is this bearing. We could go through more examples. You need to have a proper planning process so the jobs are kitted properly, planning a week in advance and all that sort of stuff to make sure jobs are being done properly. And we need to schedule the job so that the right people with the right tools at the right time are doing these jobs. And then when we actually do the installation, it's done in a precision manner using the right tools, etc. that I just mentioned, but that job has to be done properly, not rushed, but done properly. Now, on this point, we just think about it from the point of view of a bearing for a minute. This is from an SK study. Now, different studies might use different numbers. Is it really 34% of bearings failing because of fatigue? Maybe, maybe not. That's not really important. We need to eliminate this as a source. The fact is that bearings are very sensitive to load. If they're designed for a particular load, and therefore we get the designed lifetime out of it. When we put it under higher levels of load, we get much lower life. So if we double the load on the bearing compared to how it should have been designed or how the bearing was selected, we're down to approximately 12% of its life. Now let's look at how we do that. Basically anything we do that puts that bearing under greater load as the shaft turns and the balls roll around and so on, these are things we need to avoid. What can happen is under that higher level of load, in reality we actually do get a little bit of deflection of the metal. It's under tremendous pressure, but we can get subsurface defects initiating. So here I'm trying to illustrate the point. All these animations I use, I have to sort of exaggerate things just to sort of make a point. But you can see there that's kind of cracking and crumbling under the surface, and then finally it breaks through to the surface, and now we've got a spool. So, ultrasound and particularly vibration analysis can pick it up while it's under the surface. When it breaks through to the surface, we might get metal components that oil analysis will pick up. What we want to do is avoid this situation, not just detect it. We need to align properly. There's lots we can say, but again, this sort of pattern we have of the amount of alignment and the reduction in life. Now here you can see this little animation over here, just trying to sort of illustrate how just a little bit of angular misalignment greatly reduces the life on the bearing. So this is from a study you can see referenced down below. We can use dial indicators if they're used properly. They are good tools when used properly, but laser alignment is obviously a very good tool as well. We need to use belt alignment. We need to make sure we don't have soft foot problems. Precision balancing, I already mentioned before, is extremely important. The rotor might be balanced in a shop versus in situ, but there are ways to do that so that the machine runs with a very low level of residual unbalance, and it's important to do it. I'm going to skip that just for now. I'm running a little short on time here. I don't want to keep you forever. Bottom line is, as we know, the increase in load causes fatigue, which causes failure. In this case, if there's a bent shaft, we can have a situation where the shaft is actually moving back and forward, the inner race moves, puts the bearing under pressure. Here the inner race is cocked on the shaft, so maybe it was hammered into place. It's not true to the shaft. Every rotation it's harming the inner race and those rolling elements. In this case, the outer race is cocked in the housing, and again those rolling elements are put under tremendous pressure, high fatigue, therefore failure. So that's now some of that was related to installation, but the failure is because of the fatigue, but handling and installation also causes problems. Now, people installing the bearings need to really understand the importance of fits and tolerances and using the proper skills to remove bearings and install bearings, the way the bearings are stored and transported. All of these all of these issues are important. Otherwise, before the shaft makes its first revolution, there's already a problem that's going to cause the bearing to fail soon. In more dramatic cases, bits of the bearing are actually broken off, perhaps, or we get Brunelling marks on the raceway. In this case, I'm talking about false Brunelling, where, okay, this is sort of an installation process. It's also an operating process, but when we've got a stationary machine operating or sitting stationary next to an operating machine, those bearings are sitting there chattering away and causes damage. But there's lots of other things we need to consider, soft foot issues, how well we're tightening and torquing bolts, everything to do with the tightening process is important. When we're creating electrical connections as well, the order of where washers go and where the conductors are put next to each other, all of those things, often people just don't know. You may assume that all these things I'm talking about are just standard practice for the fitters and mechanics or millwrights and whatever you choose to call them. They are trying to do the right job, but if they're not given the right tools and they're never actually trained to do it properly, then mistakes are made. And very often it's just a training opportunity. You teach people how to do it properly and they think, wow, I didn't actually know that. I didn't know that it mattered if we didn't do it correctly, and I didn't know how to do it properly. Here's a case where, again, an installation issue, caused a high voltage line, arcing and so on, as you can see there. So there are other opportunities as well: improving reliability, soft foot correction, proper torquing and tightening, proper, looking at seals and gaskets, filters and strainers. Really, the list goes on and on and on and on. So they are all the reasons why we can have problems, and therefore we need to have some sort of quality assurance, quality control process when the installation work is done. So when the motor is coupled up to the pump and that job is done, then the condition monitoring guys come in and do some tests to make sure. And this shouldn't be seen as some sort of adversarial situation where, the guy doing the work, installing the bearing and so on, feels like he's being checked up on, and the vibration guy is his enemy. In plants that do it properly, they see themselves as companions. They are working for the same goal. When an installation is done, the first person that's called is the condition monitoring guy. Hey, come and check. Make sure I've done this properly. Make sure that it's all good. The test is done. Yep, it's all good, and away it goes. So lots of vibration tests, motor tests, oil analysis tests, infrared tests, and so on that can be performed to make sure the job was done properly. It's a little bit like the original acceptance testing, except that it's internal work instead. It doesn't have to be quite as elaborate, perhaps, but still, you want that equipment to be in tip-top condition after that work's done. Now, you start the machine. You hope you don't have infant mortality problems because you've done the work properly, but to assume that that's the end of the reliability issue is a mistake. We have to look at how the operator or how production is operating that machine, and then the ongoing maintenance and care of the equipment to make sure it keeps on operating in that higher level of reliability. So again, I think I said it earlier, a lot of people blame the maintenance department for reliability problems. Now, we've already mentioned the issue to do with the design process, the procurement process, the transport process, the store process, and then there's maintenance doing the installation work. But operations, the way the equipment is operated, depending on the industry, can be one of the largest contributors to reliability problems. And again, these are topics that we could talk about for a long time, but pumps were designed to be operated a certain way, a certain flow, a certain pressure, where valves are located, where bends in pipes are located, and so on. That's how it's supposed to be operated, so that the fluid, in the case of a pump pumping fluid, the the fluid flows through those impellers at the correct angle, and it's all good. Get that wrong, and the pressure on the seals, the bearings, the shaft, and the impeller itself is not per design, and therefore we reduce the life. So, I mentioned it before, but it needs to be operated at its best efficiency point. It's important. It's important, and operators need to understand that, and from a design point of view, it needs to be understood. And so that, moving from shift to shift, the equipment should be operated in the same way. And of course, that's just pumps. We can carry that story out to a lot of other types of equipment as well. Now, lubrication is important during the installation process, but obviously critically important as you continue to operate the machine. This again is a really important topic, and I've got a few slides here just to sort of drive home how important it is. But lubrication really falls into two categories. We've got the lubrication process itself and contamination. Now here, we've got 36% of failures due to lubrication versus 14% due to contamination. In many cases, the percentage of failures due to contamination may be much, much higher. But let's just look at lubrication. Any application requires a specific type of lubricant used without contamination, at the correct temperature, at the correct load. Therefore, the lubricant has to be correct. It has to be correctly specified. It has to be correctly applied. If that doesn't happen, we reduce reliability, we have bearing failures. We can have one situation where there is too much lubricant. Say, for example, greasing a bearing. You have too much lubricant, it causes potential physical damage to the bearing itself. In fact, the grease can go into the motor, for example, the motor windings. But an increase in heat reduces the effectiveness of the lubricant and reduces the reliability of the bearing itself. Too little lubricant also greatly increases wear, and that's usually the problem that we're concerned about. So, okay, this animation is really exaggerated about how lubrication works, but it is really important to understand just what a tough job it's doing. If you consider the gap between the bearing and the raceway, either the inner race or the outer race, there is a tiny gap. It is between 0.1 and 1 micron. It's really important to understand just how small a space that is. A human hair that you can see there under the microscope is 60 microns. Dust particles are 25 microns. Fingerprints, 12 microns. The smallest particle you can see is 40 microns. We're worried about particles that are more than a 40th the size that you can even see. So don't even think you can look in a lubricant and tell if it's okay. Don't think you can rub it between your fingers and see if it's okay. It's just not on. So load affects the fluid film thickness. Heat affects the fluid film thickness, and the volume of lubricant affects the fluid film thickness. We want to maintain that gap between those two elements. All it's standing in the way is the lubricant. So you might see signs of over lubrication. It generates heat, and then the heat damages the lubricant. And here we see liquefaction, and we might have under lubrication. Here I'm going to let you guess whether this is over lubrication or under lubrication. A little bit of an extreme case. Same here as well. Okay, now using our condition monitoring tools, there's lots of ways that we can make sure that the lubricant's okay. One way, in the case of greasing, is we can use ultrasound. We can listen to the bearing to see if it's properly lubricated now. As we are adding the grease, we can listen and tell if the grease is actually hitting the bearing at all, and make sure that it gets the right amount of grease. So, before, let's see, before the grease hits the bearing, we have a certain sound, and that sounds not great. That's what it should sound like. I hope you can hear that okay. You can see the waveform down below, basically what it should sound like, how that changes. And that's what an operator can listen to as they're adding grease to the bearing. It's a good technique. So let's look at contamination. That is a really big cause. Even though we've only listed it there at 14%, some studies show that up to 50% of all equipment failure is ultimately down to contamination. There are a number of possible issues related to contamination. Number one, not necessarily in this order, but the contamination can degrade the lubricant itself. The contamination can result in corrosion, so the bearing surface, because of water for example, actually corrodes the surface. So when I say degradation of the lubricant, it changes the viscosity and the properties of the lubricant so it's not able to do its job. It can increase the level of oxidation and this sort of thing. And then finally, as depicted in this a series of images here, the contaminants can actually damage the bearing surface and lead to that spoil you see. So again, it's important to understand just how small these particles are. There's a grain of sand relative to human hair. That's the smallest particle we can see. There's pollen, coal dust, and then we get down to tobacco smoke. So, there's the different sizes that we're talking about. And again, if you think about just how small these particles are, a pinhead, that's its size relative to all the other examples there. So, the fact is that different components are affected in different ways. A gearbox and other components not listed there. If you think about the particle count, this one's just a two-part particle count, it greatly reduces the life. So if we can move down that curve so that we've got, or down that y-axis, so we've got cleaner lubricant with fewer particles, you can see the life extension that we can expect to achieve compared to higher up on that y-axis. In this case, a study was performed to compare what effect different level of filtration had on life of gearbox. So the starting point was 40 microns, and you can see how many million cycles to failure you can see over there on the y-axis. The level of filtration was dropped to 25 microns, and you can see we achieved, well, the study achieved a slight improvement in the number of cycles to failure. 10 micron filtration, still it's increasing. 6 micron filtration, 4 micron filtration. You can see a dramatic difference when you get down to that sort of 4 micron filtration level. That means if you're using just a 40 micron filter, or even a 10 micron filter, it may not be enough. Well, looking at this, and from experience, it is not enough. You've therefore got to stop the contaminants getting into the lubricant in the first place, and then your filtration has to get them out. And this is one of those points where people sometimes say, yeah, but I use a filter. I tried a 4 micron filter, but it kept getting blocked. Well, that's just because you have so many contaminants in the lubricant that the filter got blocked. You don't need to sort of fall back and use a worse filter. You need to clean up that lubricant, find out how the contaminants are getting in there, and eliminate that as a source of failure. Now, when we think about the particles, there will be some particles that just kind of get squashed by the rolling elements. Everything I'm saying here, by the way, this is bearings, but gears are exactly the same sort of situation. There may be some particles that go between the two surfaces. They may cause a little deflection, but not actually damage the surface. But ultimately, there are hard particles that are of a certain size that cause damage. Now, remember, this is sort of 1 micron, or particles that are very small, let's just say. The gap there is 1 micron, but it takes quite a small particle to get sort of jammed in that space. Much bigger particles, those 40 micron particles, are often just being pushed along by the bearings. They're much bigger than the gap. Same with the gears, although the operation is a little bit different in that case. In some cases, the particles are being pushed along and they'll score or damage the surface, as I'm trying to depict in this animation. Anyway, contamination or contamination control is extremely important. And so sometimes we just have to look at the equipment and see why we're getting contamination. Imagine trying to put grease into that nipple there. How much is going to be pushed in unless it's properly cleaned. Not to speak of the overheating that's going to go on and everything else. Some people believe that the lubricant they buy and that they store on site is good and clean and fit for their machine, and that maybe the contamination comes later. So try this experiment. So here's a filter bag. Take a sample of oil, pour it through, and that's what was found in the filter bag. Now remember, those particles you can see, they're very large particles. There are lots and lots of really small particles as well, and potentially these larger particles will be broken up to create the smaller particles. Now, we haven't spoken in detail about all the different types of contaminants, but water is terrible for corrosion and terrible for the lubricant itself. Well, when you store those drums outside, as they heat up and cool down, heat up, cool down, it just sucks the moisture out of the air, and of course if there's rain sitting on top, it sucks that in too. So you really need to take care of these things. So, there's lots of ways through perhaps desiccants, through storage techniques, making sure the right lubricant is put in the right machine. That's a big deal. Sometimes you look inside a bearing and you can see that it's received 4 different types of grease. Generally, those greases are not compatible and you create a problem. Sometimes completely the wrong oil is added to a gearbox. In one case, the person was using a lower grade oil just because it poured in faster. Things like that. There are ways around these problems. It's not rocket science. It really isn't, and doesn't have to necessarily be all that expensive either. But the change to reliability, and therefore the breakdowns, and therefore the costs and everything else, it's a substantial issue. So just one little point, on the filtration. It's important to understand how these filters work and what beta factors mean, because even though you can say, well, I've got a 10 micron filter, you need to consider the effectiveness of the filter. How many particles are actually getting through that. Okay, there's a certain size, but how many? Anyway, we won't dwell on this for too long, but it's really important to understand these sorts of things so you know really what you're getting into. Okay, so when we talk about oil analysis, it's just worth dwelling on this just one more little point. That number one, the oil analysis is there to check the chemistry of the lubricant, to make sure that the viscosity is okay and that the additive packs are okay, to look at oxidation and to look at the small particles. But number one, it's there to look at the chemistry. So this is condition monitoring, but we can perform, if you like, condition-based lubricant change. If we allow substandard lubricant to remain inside the machine, it leads to reliability degradation in its reliability. It will lead to faults. Likewise, we can use our condition monitoring technologies to check for contamination, water and particles. And we can check the particles themselves. We can look at the color, size and shape of those particles. Now, in the last case, that is both a case of looking at the source of the particles, but also what sort of wear is happening, and then we can get a condition sort of assessment. Bottom line is that we can use these technologies to not only be used in a traditional sense of what is the condition, but also if we're proactive about it, we improve reliability, and that's ultimately what we should be seeking to do. And of course we got to perform the tests and so on. Now, another important point to make is that, while the machine is operating, the alignment state, the balance state, and other things will change. We need to make sure that the machine is balanced and aligned, and that's where we come into sort of the final stage of the quality assurance and quality control. This is really our traditional condition monitoring. Now, we can go around and take measurements and look for faults, the normal sort of routine that we go through. However, again, with reliability in mind, we should be looking at things like looseness, misalignment, and unbalance. And think about not just, is the alignment so bad that we need to correct it now? Is the balance so bad that we need to correct it now? We need to think, is it bad enough that it's going to degrade the reliability of the equipment and lead to faults later on? So let's say we perform a test and we see that there is some misalignment or there's a little bit of unbalance. We might consider that, from a fault condition point of view, it's okay. But if you make that call, you just have to now wait until that bearing fails. You can sort of expect that the bearing will fail prematurely because every single rotation is being pounded because of the misalignment or the looseness that's going on or the resonance which is something that should have been corrected earlier in the case of the resonance. But unbalance can develop over time, and so therefore as part of your condition monitoring program, we need to eliminate that unbalance. Everything has a priority, everything has a cost. In my opinion right now, these sorts of things don't get much of a priority. In fact, they're not even looked at. The condition monitoring person won't say anything about unbalance until it gets quite bad. That's something that I think needs to change. It's then a case of waiting for an appropriate opportunity to perform the balance. But if there can be in situ balance, there might be an opportunity, because the machine's being shut for something else. Alignment can usually be taken care of quite quickly when the machine's being stopped for something else. I'm not saying you're going to stop the machine to do that sort of work when the severity is not very severe, but you can certainly take the opportunity when it presents itself, and you will get longer life out of that machine. So again, summarizing some of the condition monitoring that can be used that will lead to condition improvement, again with the oil analysis, but we can detect poor lubrication practices, looseness problems, the unbalance, misalignment, a bent shaft, eccentricity and so on, resonance. We can detect if the bearings haven't been installed properly. We can detect cavitation and turbulence. We can test for hot spots and poor terminations and insulation problems and so on. We can use our condition monitoring skills to detect these problems, and if we do something about them, we improve reliability, and that's where we get the biggest bang for the buck. So, of course, at the end of all of this, we should mention root cause failure analysis, because when there is a failure, we can use root cause failure analysis to determine why and see how it slipped through all these things we've put in place. But it's going to be common. There will be faults, and you need to assess why it occurred and then decide, well, is it feasible to change our practices? Is it justifiable to change the practices? But one thing to say, what are you doing right now with the bearings that you remove? The vibration analyst reports a problem. Is the bearing simply pulled out, scrapped, and another bearing put in? Does anyone actually look to say, well, what caused the bearing to fail? Now, you can look at the surface of the bearing and you'd be amazed what you might see. In this case, is water is pulled up around the rollers while the machine was stationary, but you can see all kinds of patterns which indicate misalignment, false Brinelling, EDM where there's current going through the bearings. lots of things. It tells a story. Okay, now, we've been talking a long time. I hope this is proving useful for you, but there's a few more things to say. It's okay to talk about all these opportunities you have to make some improvements, achieve better reliability, which reduces the costs. How do you implement this sort of a program in your organization? It's often sort of considered that there's a sort of a bow wave effect, that there's a certain cost associated with making these improvements. So in this case here we've got an investment which is in red, and then a savings is achieved and there's resulting profit afterwards. Now this was in a particular presentation, so I'm sort of showing it how it was presented, but I would say that it's all based on definition. But let's just say, okay, we're going to aim for 80% condition-based maintenance, 20% proactive and planned, and so on, and as few breakdowns as possible. But the fact is that a manager might say, or a senior management might say, well, I'm not willing to invest that much and wait for 2 years for a break even. The thing is, now, there are ways, without investing as much, really the red part should drop down, where you can make small changes and reap the rewards more quickly. So you can just make these smaller incremental steps, invest a little bit, in some cases not at all, it's just really a change of practice or something like that. But you can make these small investments, get a reward, small investment, get a reward, and senior management can see the value in this kind of philosophy. So this is important. But the question is, how do you go about it? What's the overriding principle here? Number one, you can go to senior management and say, I've seen the light. There is a way we can make some really dramatic changes in our plant. We can achieve the lower costs and higher levels of revenue and so on that I described at the beginning. And you can get that corporate support. In my experience, the plants that have the greatest success do go down this path. They get that senior level of support. And when everyone from the plant floor up recognizes that senior management believe this is important and they're supporting it, that's when change will happen. There's an excellent business case to make. As I just described, you don't have to make really large investments, so it should be possible. Sometimes, however, people are concerned about that approach because maybe it puts too much focus on what they're doing and there's too high expectations. So another way to do it is what I call reliability by stealth. It's sort of flying under the radar a little bit, just taking small projects and, as we say, getting some runs on the board. Have some successes, report those successes. This is a really big topic. It really is important to get that corporate level of support, but if you don't think you can get it, or you really, really personally don't want it, just make sure you are recording before and after scenarios. So don't just sort of make these improvements and say, hey, I did this and see our current status, it's better than it was. It really makes more sense to do benchmarking and so on and say, okay, well, this is how many failures we're having, this is how many motors and bearings we're going through, these are our statistics related to capacity and availability and whatnot. Any piece of information you can get so that you can say, this is the situation now, we implemented an improvement and these are our results later. That makes it a much more compelling story that you take to management. Okay. The really important point is that if you think about all the things that I've said, I hope you will agree that none of them are rocket science. None of them require huge investments. You don't necessarily have to do some huge RCM analysis to recognize those problems. If you think about all the things that I've just said, if you can, with hand on heart say, we've already taken care of all those things. We don't have contamination problems, installation problems, procurement problems, and all those sorts of things. Well, I probably can't help you, and you may need an RCM program to really, really get to the bottom of reliability problems that are more unique to your plant. However, more than likely, if you're listening to this, that's not your situation, and you need to look at all of those suggestions and get the training where necessary, get the equipment where you don't have it, and make those changes and improve the reliability. And you can start recording mean time between failure properly. There's a lot of other things you can record as KPIs to sort of monitor the progress that you're making and identify the opportunities. But really, I don't want to say it's trivial or anything like that. It's just not that hard to make some of these sorts of improvements. There is a big barrier, and we're about to talk about it. But one of the starting points is to do a plant walk down. Find the low-hanging fruit, so to speak. Look at the levels of cleanliness, the tightening practices, the alignment practices. How many leaks do you see? How many steam traps do you see spitting out steam and so on? What's the status of the way the lubrication is done? How the lubricants are stored? What the reservoirs look like? Are they open? What's the status of the breathers? Are you performing unnecessary overhauls right now? Do you see signs of rust, and is there other signs of corrosion? Do you have standards or specifications when it comes to balancing and alignment and all those sorts of things? You can do a plant walkthrough and find all these opportunities, then prioritize them. You can determine which ones will give you the biggest bang for the buck and go after those. So personally, as I mentioned, I think it is worth getting that corporate approval, getting that support from the top. I think it's important to perform some benchmarking, so you identify your starting point, set some targets, and therefore you identify your gaps. And establish some KPIs, set some goals, and communicate your successes. So as those KPIs go in the right direction, you record those and report those. Now, so far, everything we've discussed has been technical in nature, installing bearings properly and doing all the rest of it. There's been one big gap in what I've described so far. What have we forgotten so far? It's the people. It's the issues with the people. It's the reliability culture of the plant. And that's what you have to change. Yes, you can take on these little technical issues, but for example, people go out and buy laser alignment equipment, but it's not used. Vibration equipment's purchased, it's not used properly. Containers are purchased for proper lubricant dispensing, but they're not used properly, they're dirty, etc. Why does it always feel like it might be you against a whole lot of people in the plant? Why don't they seem to get it? Why do they resist the change? Why is it so hard when you know that it makes good financial sense? You know that the concept of reliability is easy to grasp. Anyone who owns a car knows that they want high levels of reliability, and they're usually willing to pay to get it. And we know that everyone benefits. Now, some people might argue, hey, I get overtime on Sunday when something fails. You've got to demonstrate that there are safety issues, there are financial issues, whether or not you want to say, look, there's even a possibility that the plant will close. You've really just got to really take that option away and say, no, we are going to be reliable. We need to stop that. We need to be able to talk about these topics without feeling like people just don't want to hear what we're talking about. So just think about a few things, And when I talk about culture change, obviously this isn't religious or anything else. It's just the reliability culture. It's just the way things are done in the plant. What is the attitude in the plant? Are they being rewarded right now for the unreliability? Is reliability important to them? Now, when I say rewarded for unreliability, that's the overtime on Sunday. That's the the huge pat on the back and the congratulations when the maintenance guy gets a machine up and running. It's not to say that a person doesn't deserve that congratulations, but if that failure was premature, if that failure was due to poor operating practices or maintenance practices, you need to consider that those repairs and that emergency work is really something that no one should be proud of. But the flip side of all of this, it's one thing to say, well, that person, we need to treat that person in terms of not rewarding them for unreliability, but you know what? We also have to go to that person and say, hey, you're the one that spends all the time with the machine. Can you give us suggestions? But when they give us a suggestion, we have to listen to it. We have to act. Now, this doesn't mean we accept every suggestion and make the requested change. But if we don't, we better go back to that person and say, look, thanks for the suggestion. This is the reason why at this time we can't do it. Be it technical, be it financial, be it whatever. But ask them their opinion and make sure they're given the correct tools, time and training to do the jobs properly. It's no good blaming people for reliability issues and then you find out, well, they haven't even been given the proper training to install bearings properly and so on. Culture change really is the key to reliability improvement. People want to take pride in their work, and they will take pride in the work when this culture is changed. Not overnight, but anything you start today is going to happen more quickly than if you just keep putting it off. The attitude needs to be, we will get it right the first time, because we know that little bit of extra time we take to get it right now means the machines operate at a much lower cost and higher level of reliability. And also, with proper planning and scheduling, sometimes it doesn't necessarily have to take longer. A lot more time is wasted right now with poor or no planning and scheduling. And part of it is that people have to see that just because they're normally fixing machines in a reactive sense, what you've got to say is, okay, now you're going to be working on tasks that are proactive in nature. Performing tasks that improve the reliability of equipment, performing inspections, performing proper lubrication, etc., 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 that ultimately leads to improved reliability, not just reacting to problems. And they might even get involved with condition monitoring or something else. You've then got to say, well, what is the attitude of senior management? Because if you've got senior management with a bit of a dogmatic approach and talking about firing people and looking at cost cutting and not believing in reliability, well, then you can have a real mixed message. You're sitting there talking to them about training for awareness and training for improvements in way bearings are installed and so on, but if that isn't the culture of the plant being driven from the top down, then people will just resist and say, this is just another fad. This really isn't a change going on in the plant. This is just, you being over enthusiastic about this particular issue, and you're trying to get me to change. So, we need to make sure that senior management appreciate the value and importance of improving reliability. And it's not a hard sell. There's so many compelling arguments, as I sort of went through right at the beginning of the presentation. They have to make reliability a priority, ideally with some sort of statement. Just as there might be a statement regarding safety, how safety is our top priority and so on, reliability needs to be right there alongside it, because they're related apart from anything else. And that might mean that they have to provide the funding. Well, it is going to mean, you can't add filtration and special lubricant storage devices and buy vibration analyzers without some sort of funding. But anyway, so you need that top level of management support, so that if they are saying reliability is critical to the success of the organization and everyone must be properly trained and equipped to do the job properly, then you'll see some changes. That's the message they need to hear. If you don't deal with the culture change, then all the technology and all the training will be for nothing. It just won't make the difference. So, having said all of that, let's have a look at some of the reasons why programs do fail. Now, some of these things I mentioned earlier, so I won't dwell on them, and you can, of course, pause the movie if you like. But I think that part of the problem is that people start with a really heavy analytical approach. They spend a lot of time and money trying to analyze the reliability rather than actually trying to improve it. And then they're using that information to make decisions where the reliability data is not reliable. So that's an important one. I also see companies that just dive straight into classical RCM, and these, the focus on RCM, number one, is maintenance. It's about developing maintenance tasks which will, properly maintain the equipment and keep the equipment running. But often the study is never completed, work practices don't change, and employees don't accept the recommendations. A lot of program, after studying this equipment and the next piece of equipment and the next piece of equipment, it's just really hard work. And the sad fact is, now this is just one pretty good study that was performed. 15% of projects succeed. Now, the definition of succeed, you could look at, but even in the ones that did succeed, often there wasn't really reliability improvement associated with it. So I'm not saying don't do it. However, you need to be forewarned, and I think that there is an efficient way that you can make key decisions so that you can start making improvements today. And then maybe on just the 10 or 20% of most highly critical equipment and equipment that proves to be, still have poor reliability, then you get more formal with your RCM and FMEA and so on. I mentioned that senior management support is really important, but if you don't get it, then that's a common reason why programs fail. And sort of getting past those first couple of issues, a lot of surveys that we've done, when we've said, okay, what's holding you back? It's senior management support. This issue of the wrong emphasis being placed on reliability data and these sorts of things, that can cause a program to fail. There can be reliance on interval-based maintenance. Sometimes companies that have reactive maintenance think, okay, well, the most logical thing to do is not too much go to planned maintenance. Planned maintenance is important, but treating everything as if it is age-related failure, and therefore repairing quote-unquote healthy equipment, performing intrusive inspections that cause harm to the machine, performing tasks that were unnecessary, etc., etc. It is all costly. It is all I shouldn't say it's all counterproductive, but a certain chunk of it is. Then we get down to the point of this actual presentation. That the primary focus is on condition monitoring. Now it is important to detect faults for sure, but there needs to be an understanding that it is intended for condition-based maintenance, not just reactive maintenance with an earlier warning, and we have to use the condition monitoring technologies to improve reliability, and we also have to write reports that are easier to understand, that people can take action on, and so on. Now, this one is a sensitive issue, and if you're a consultant, I'm probably about to offend you, and I apologize for that, but there are consultants who do a great job for organizations because perhaps the program is driven by the client, but the consultant comes in just to help them. So the client says, okay, we recognize we have a contamination issue. Maybe I'll get you in, consultant, to do a bit of an audit and make some recommendations. Now, if the client needs that help, then great. Get in that person with experience to help make those decisions. The programs that I see fail is where they basically hand it over to the consulting company and say, make this problem go away. It's a big problem. We recognize the financial benefits of improved reliability and so on. So now I want you to take control of this thing. The trouble is that often the culture of the plant doesn't change. The skill levels and knowledge and buy-in doesn't change. Sure, you get experts to come in and they will make some changes and they will make some improvements, but one day they have to leave. And what happens when they leave? All those old bad habits start up again, and it's been seen again and again and again. You have to make sure, if you're going to use consultants, that the number one goal is sustainability of the program, and that the people at the site are the ones that are going to take responsibility for their own plant and go on with it. They have to be trained to do all these things. Let the consultants show you how to do it. Don't just let them do it. Again, that's my opinion. I think there are a lot of in-house initiatives, and in my personal opinion, that's the best reasons for the reason that's the best approach, for the reasons I've just explained. However, where they often go wrong is that there's ineffective internal training. You will get 1 or 2 or 3 people that are very enthusiastic, that might take some training, that might get certified. They go to some conferences and they think, great, now I'm going to try and wrestle all the other people in the plant to make these changes, to make these improvements. They're going to start a condition monitoring program and make these little improvements, but it's just not sustainable. There's no real plan. Sometimes people make a start and it gets a bit complicated, and being scared off is a bit of a harsh word perhaps, but they see it as too much of a challenge. And then there are other issues. For example, there's no asset register or master asset list. There's no asset criticality ranking. They're searching for the quick fix solution, looking for something that's just going to make it all work overnight. There is no quick fix solution. This isn't a project that you do over the next 2 weeks or even a year. This is a new way of life at the plant. This is a new way of life, and you have to make those changes bit by bit. You have to bring all the people along with you. So you can't be too impatient. You have to have a focus. You have to say, well, this is what we're striving for, but we're going to do it one step at a time. And you have to be willing to make changes to bad practices, whatever they are. You have to take people on. There's a way to do it so that they feel part of the process, and that they actually even suggest that they need to change. But these things need to happen. And of course, some programs fail because you never really did get management buy-in, and they then kill the program, or you get a new manager who comes in, new CEO or whatever, comes in, doesn't appreciate the value of reliability improvement, wants to make a name for him or herself, thinks they can save a bunch of money, and they kill the program. And, for the next little while, the books look better because maybe a bunch of people have been let go, people aren't going on training, etc., etc., etc. For a little while, it's a great financial strategy until all those reliability problems raise their ugly heads again, and they are ugly, and they will raise their heads, and the problems start up. So it needs to be part of the culture, just as a manager wouldn't come in and say, right, forget all these stupid safety practices, it's just slowing us down. They shouldn't also be allowed to get rid of the reliability practices. Okay, I will say right now, I am biased in this regard. I run a training company. I believe in education. I believe that education is the root cause of all of these problems. If people understood the ramifications of the way they're operating the machines, the way they're purchasing equipment, the way they're designing, the way they're maintaining, the way they're everything. If you understood how those practices are causing the problem and the benefits that can be achieved by making changes, then the changes will occur, and that is only going to happen through education. Education really is the enabler. Like I say, I am biased, and I'll say that right up front. Now, just on the training issue, we, for example, offer what I call conventional training. A person goes off-site, goes on a training course, and they learn something. And that's great. You get a person who needs some really special skills, and they can go off-site and they can get those really special skills. But what can happen is that person goes off-site, they learn a lot, they come back though and they're still working in a plant that doesn't get it, that doesn't have their belief in condition monitoring or whatever they were just trained on. So I don't believe it's possible to slowly send people off to different training courses and have people come on site for training courses. You get some people who learn things and they forget things. They have all these good intentions after a conference or a training class, but it kind of gets beaten out of them when they're dealing with all the people who haven't had that training. Training needs to be synchronized between departments, but also between sites, ideally. Sister plants should also go through the right sort of training. The training may be inconsistent. You get different messages from different people. Sometimes the training's boring. It's really important, in my opinion, that the really specialist training can be achieved through conventional training, perhaps, where it's not available any other way. But for a large part, the training needs to be provided to everyone in the plant so that at the same time everyone comes up to speed with what this is all about, what the new order is, what the new reliability culture is within the plant. Now, I'm going to just make one little final dig there, this Trojan horse training. Again, it's just a personal comment, but there are a lot of companies that come in that say that they are a training company and that they are there to train you. But I like to have a little joke and say that sometimes those consulting companies that offer training are sort of like Trojan horses. They come in to say, we are here to teach you, but their ultimate goal is not to educate you so that you can do it properly. It's to create a consulting opportunity. So they come in and they tell you some of what you need to know, but potentially they make it all sound so complicated that it's out of your reach to do it, and lo and behold, they have services and they can do it for you. So look, I've seen it so many times, and yes, I'm biased because we offer e-learning and all that sort of stuff. Yes, I am biased, but you just got to be careful, because those people who come in as trainers, you got to make sure that they're not also coming in as really just consulting salespeople who ultimately just want to do it themselves. Okay, how many people have I just offended? Okay, so last but not least, the key implementation issue. I talked about the bow wave before, and that's important, and there's a lot we could talk about the bow wave, breaking it up into lots of smaller bow waves and so on. But we can get to a point, and we can, if we work hard at this and do all the things that I've discussed, I believe you can achieve these goals. And then you will, keep operating in this new way. You can keep making new improvements and so on, but you just need to be diligent and say, this is the new way of working. You keep doing acceptance testing, keep doing proper lubrication, keep doing all these things. But beware the manager who comes in to save money, because if they come in and they think, oh, we can save money by firing the reliability people and stopping the condition monitoring and buying less expensive motors and pumps and all the rest of it, you will be back to that unreliable state faster than the time it took to improve reliability. And that situation has happened again and again and again and again in over the history of lots of plants. So just be warned. So condition monitoring is great. Detecting faults is great. But we need to look at ways we can use condition monitoring for prevention. Detecting conditions that will lead to faults and eliminating them. Using condition monitoring for acceptance testing and testing after maintenance has been done. Looking at care, proper lubrication, proper operation. Performing precision maintenance, the way we install equipment and bearings and so on, balancing alignment, tightness. Look at the way inventory management is being handled, planning and scheduling, transportation and storage, and the design and procurement process. So yep, condition monitoring is important. Condition monitoring is incredibly valuable, but really I believe you need to look at this bigger picture in order to improve reliability in the plant. Well, thank you very much for viewing this movie. I hope you found it useful. If you have any questions, you can see my email address there, but feel free, if you just have general inquiries about Mobius, just send an email to learn@mobiusinstitute.com, or just go to mobiusinstitute.com you'll find other videos and all sorts of good things. So thanks again for taking the time to go through this rather long presentation, but I really hope that you found it useful.